Hello students, welcome to section 6.4 part 2. The last time we were together we were discussing the definition of vector components, of which you can see in this particular depiction that W1 plus W2 will be added to equal this U vector. When I carry that over into this particular depiction below, we talked about how W1 and W2 are orthogonal. In other words, they are perpendicular to each other, as this depiction also shows. Not just in this picture, but also in this picture. As it turns out, theta, which will be the angle that we will take a closer look at in context, theta will be the angle that's formed between vector v and vector u. Not just in this depiction where it's acute, but also in this depiction where it's obtuse. Notice in this particular picture here, we've got W1 parallel to V, but in the same direction. While here, V and W1 are also parallel, but in opposite directions. Notice here that theta is obtuse, again the angle between V and U, while here again it's acute. It's notable too, again, that W1 and W2 are perpendicular or orthogonal, as U will take shape as a result of the two added together. As we continue, we talked about how projection vectors are going to play into things. The vectors W1 and W2 are called vector components of U. The vector W1 is the projection of U onto V, where U and V are non-zero, and it's denoted by the following. W1 is equal to the projection of U onto V. Now, if we go back to this first depiction, one of the ways to help you remember what the projection of U onto V really means is envision, if you will, this U vector maybe representing something in the outside world where the sun maybe strikes the vector, could be an object actually, and forms a shadow. So vector U, again, imagine, if you will, maybe a shadow that's formed, let's say, by some light source hitting U and creating this shadow V. This is the projection of U, but onto V, we say. And the same goes here. It's a little bit more complicated to show a projection such that it's off in this particular manner. But in theory, I guess, if we're talking about a light source coming in from this particular direction, V would be possibly the shadow or the projection of U onto V. And in both instances, that's how it's essentially taking shape. And we're going to go ahead as we continue, noting that the vector W2 is given by simply the difference of U minus W1. We discussed earlier that W1 plus W2 is equal to U, so it makes sense that W2 is the difference of U and W1. In the above definition of vector components, it is easy to find the component W2 once you have found the projection of U onto V, which again ends up simply just being W1. To find the projection, you can use the dot product. So here's the formula for W sub 1 for the projection of U onto V. It's the dot product of U and V divided by the magnitude of vector V squared times its component form vector. In example 5, we'll go ahead and take a look. Although we won't be necessarily drawing a picture for this, you can, to help you kind of frame your understanding. Find the projection of U, which is 5, 2, onto V, which is 3, -1. Then write U as the sum of two orthogonal vectors, one of which is the projection of U onto V. So let's go ahead and take a look. The math behind this is fairly straightforward. You stick to the formula, wherein if we actually use the formula, as you see, W sub 1, again, is the projection of U onto V. In other words, the dot product of U and V, so it's 5 times 3 plus 2 times -1. There you go in the numerator. The denominator, you can see then, is the magnitude of vector V squared. So the square root of 3 squared plus -1 squared, and that whole thing ends up being simply squared. And then that multiplied by the component form of vector V. The math, when you perform the operations, simply end up being in the numerator. You'll have 13 tenths. Times this component form again, 3, -1. 13 tenths is the simplified version of this. If you go through, you'll find 9 and 1, of course, add to 10, the square root of which is 10, but squared is just 10, and the numerator, that's just 13. So if you distribute 13 tenths to this vector component form, here's your W1 vector. Now, as we discussed, again in the picture up above, W1 plus W2 is equal to U. Now that we know that W1 is this component form, we can go ahead and find W2 simply by subtraction. Simply U, which we again know to be 5, 2, minus this vector, as we just said, W1. So W2, if we do the analysis, we can subtract. We have 5, 2 minus 39 tenths, negative 13 tenths. 5 minus 39 tenths ends up being 11 tenths, while 2 minus a negative 13 tenths is 33 tenths. So this is in fact the W2 vector when it's all said and done. Now, if we take the connections that we've made earlier and we apply them here in context, if we were to check, in other words, if we were to say, is U equal to W1 plus W2? Well, let's see. 5, 2, is that equal to W1 plus W2? Well, of course it should be, and you'll find that, of course, you'll end up with that particular result. Okay. All right. So let's continue on to the next page. So why are we using projection vectors? Projection vectors set us up to do problems of which we have done in the past using simply SOHCAHTOA. Well, projection vectors may take the place of SOHCAHTOA if you find your projection vector set up to be simpler. We'll go ahead and do both. Here's the example. A 500-pound piano sits on a ramp that is inclined at 45 degrees. What force is required to keep the piano from rolling down the ramp? We have done a problem like this before, and yes, we did use SOHCAHTOA. So let's refresh our memories as to how this is going to take shape. And what I am going to do here, as you can already kind of see, not surprisingly from what we've seen in the past, we're going to frame our perspective to where this is the piano, this is the ramp, okay? Here's your 45-degree angle. There are force vectors here of which I'm denoting U as the weight of the piano. The force vector straight down is always the weight. In this particular case, it's U. And you've again seen me in the past denote that vector as far as its magnitude, aka length. In this particular case, we know as 500. The 45-degree angle, but also some 90-degree angles here and here, here and here, and then also here based upon some of the other force vectors, W sub 2 and W sub 1. W sub 2 is the force vector against the ramp, and then W sub 1 is the force that is equal and opposite to the force that you're going to use to push the object, or in this case piano, up the ramp. So here's your depiction off to the side where you can see 45 and 45 based upon this angle, of course, being 45, noting that that's also 45, and of course that also would have to be 45. So it's nice that you have a 45, 45, 90 right triangle here. As a matter of fact, you've got several of them. Again, W sub 2 is the force perpendicular to the ramp, while W sub 1 is the force that will be required equal and opposite to keep this piano from sliding down. You want to push it up. So equal and opposite will at least hold it on the ramp at that point. Okay, so we are going to use SOHCAHTOA for choice or option 1. And I think it's pretty clear that when you use SOHCAHTOA here, we're going to use that picture. And we can see that W1 would be equal to, if you look at it, sine of 45, I should say, is set up to where W1 over 500 opposite over hypotenuse. So for finding W1, we're looking at maybe this angle here, the sine of which, again, 45 is opposite over hypotenuse. We can do the math simply by multiplying 500 times sine 45. So the W1 force vector, again, the force that's required to keep the piano from rolling down the ramp, is simply 353.55. If we were to push with an equal and opposite force to W1, you could actually think of it as a V vector. Okay, that V vector, if in fact it is greater than 353.55, the piano will start to slide up the ramp. If V is less than 353.55 pounds, the piano is going to slide down the ramp. Okay, in order for it to just stay as it is up on the ramp at that point, it will have to be equal to exactly that particular weight in that particular direction. Technically, it's equal and opposite if you're going to keep it from rolling down. Okay, let me go ahead and use projection vectors though, because projection vectors are a little bit more interesting to kind of put together in context here. And certainly we can use this to solve the problem just as easily. So W sub 1, remember we had said earlier, is the projection of u onto v, which is the dot product of, if we recall, u and v, go back up here, divided by the magnitude of the vector v squared times the component form of vector v. Now vector v in the context of the problem will end up being this ordered pair. Okay, vector v, if you think about framing our xy axis, where this ordered pair is, you can call it actually 0, 0 in context, so the xy axis would take shape here. Okay, the ordered pair of the v vector, which would be here, would be negative root 2 over 2 comma negative root 2 over 2. So if we do the dot product, I want you to take a look and pay attention to 0 comma negative 500. 0 comma negative 500 would be the ordered pair of this u vector, while negative root 2 over 2 comma negative root 2 over 2 would be, again, the ordered pair of the v vector. Again, the vector equal and opposite to w1. Okay, we can also consider v as parallel to w1, as we saw in our prior depiction here. We talked about v and w sub 1 being parallel to each other. Okay, technically we want them to be equal and opposite in nature, but again, the projection of u onto v will work out regardless if we denote the orientation, I should say, of v with respect to w sub 1. Anyways, the math that you do here, which I will show, and you can double check, and notice the denominator is the component form of v squared, the square root of which, the magnitude we know. And in the end, you'll end up with the following. You can double check, but 250 root 2 will be that resulting scalar times this particular vector in component form. And if you distribute, you will find that the exact answer, as we saw up above, takes shape. This process does take a little bit longer than this, unless, of course, you're asked maybe to use vector forces like v in the future, which you may be asked to do so. In the end, the component form ends up being this, and when you take the square root, as we know, w sub 1 using the x sub 1 and x sub 2 coordinates squared, or w sub 1 squared, w sub 2 squared if you prefer. Anyways, the square root of that ends up being 353.55 pounds. Let's talk about work. The work done by a constant force F acting along the line of motion of an object is the following. W, work, is equal to the magnitude of the force times distance, or the magnitude of the force vector F times the magnitude of the distance vector PQ. So let's observe the following. Imagine, if you will, you're pushing an object, a box, let's say, across a surface horizontally from point P to point Q. The force vector, let's say, is exactly horizontal to the ground, of which, again, from point P to point Q, the box is traveling. This representation could be used in the context of this particular formula. However, let's say maybe the force vector isn't horizontal. Well, in this particular instance, and notice projection vectors play into things. Again, from point P to point Q, however, the force vector is at an angle. That angle of which we're denoting here as theta, is the angle formed between the projection of force vector F onto PQ with, again, respect to the force vector F, giving us that theta as we can see. When we finish this idea, we'll take a look, and on the next page I'll formulate the precursory info for the example for you to try on your own. Here's the work formula. The work is equal to the projection of force vector F onto PQ, the magnitude of which is multiplied then times PQ vector in its magnitude. And this is also equal to the cosine of theta times the magnitude of F times the magnitude of PQ vectors, or F dot PQ. This is an alternative way to do it. I ask that you do example 7 using this or this version. Actually, there's 3 versions to look at. Technically, the one with cosine will be the one you'd like to try. Try example 7 and compare it against the answer.